73. That number, 73 kilometers per second per megaparsec, is one of the most precisely measured and most deeply troubling numbers in all of modern science. It is the rate at which the universe is currently expanding. For every megaparsec of space, roughly 3.26 million light-years of distance, the universe stretches itself by 73 kilometers every second. 73, measured with extraordinary precision, confirmed by multiple independent teams using different instruments and different methods, a number that by now should not be controversial. And yet, when cosmologists look backward, when they use the best models of the early universe, the most refined understanding of the Big Bang, the most sophisticated equations of fundamental physics, they predict a different number. Not 73, but 67. 67.4 to be more precise, a difference of about 8%. 8% does not sound dramatic. In everyday life, 8% is rounding error. It is the difference between a good tip and a great one. But in cosmology, in the science of the universe as a whole, 8% is enormous. 8% means the models are wrong. 8% means something is missing from our understanding of reality at the most fundamental level. 8% means the universe is doing something that our best theories cannot explain. And it has been doing it, apparently, for the entire history of the universe. This is what physicists call the Hubble tension, and right now, in April 2026, it is one of the most urgent and most unsettling problems in all of science. Welcome to GreenTea English. I am glad you are here. Pour your tea and let us think carefully about what this means and why it matters far beyond the world of physics. To understand the Hubble tension, we need to begin with a man who did not believe what his own equations were telling him. In 1915, Albert Einstein completed his general theory of relativity. The equations were beautiful, the mathematics was exact, and among the many things those equations described was the behavior of the universe as a whole. And the equations said something that Einstein found deeply uncomfortable. They said the universe was not static, not fixed, not eternal and unchanging as almost everyone assumed. The equations insisted that the universe was either expanding or contracting, that it could not simply sit still. Einstein was so troubled by this that he added an extra term to his equations, a kind of mathematical fudge factor specifically designed to make the universe stay still. He called it the cosmological constant, and he later described it as the greatest blunder of his scientific career. Because in 1929, just 14 years later, an astronomer named Edwin Hubble confirmed what the equations had predicted all along. The universe was expanding. Hubble had been studying distant galaxies, measuring the light they emitted and noticing something strange. The light was shifted, stretched toward the red end of the spectrum in a way that indicated the galaxies were moving away from us, and not just moving away at speeds proportional to their distance. The further a galaxy was from us, the faster it appeared to be receding. This was the signature of expansion, not galaxies moving through space, but space itself stretching, carrying the galaxies with it like raisins in a rising loaf of bread. Every raisin moving away from every other raisin, not because any of them are running, but because the bread between them is growing. The universe, it turned out, had a beginning, a moment of extraordinary density and temperature from which everything we see, every star, every planet, every galaxy, every atom in your body had expanded outward. We call that beginning the Big Bang, and it happened approximately 13.8 billion years ago. This much is established. This much is not in dispute. The universe began, the universe expanded, and it is still expanding today. The question that is currently tearing cosmology apart is not whether it is expanding, but how fast. There are two ways to measure the expansion rate of the universe, and they give different answers. The first method looks at the early universe, at the faint afterglow of the Big Bang itself, a bath of microwave radiation that fills the entire sky, called the cosmic microwave background. This radiation is a snapshot of reality when it was approximately 380,000 years old, ancient beyond comprehension, a photograph of reality before any stars had formed. By studying the patterns in this radiation with extraordinary precision, using satellites like the European Space Agency's Planck telescope, cosmologists can reconstruct the conditions of the early universe with remarkable accuracy. And from those conditions, using the standard model of cosmology, they can predict what the expansion rate should be today. That prediction is 67.4 kilometers per second per megaparsec. The second method looks at the local universe, at objects close enough for us to measure their distances directly, using a chain of cosmic distance markers called the cosmic distance ladder. Cepheid variable stars, whose brightness pulses in a regular rhythm that betrays their true luminosity. Type 1a supernovae, whose peak brightness is so consistent they function as standard candles across billions of light years. By measuring these objects precisely, by calibrating each rung of the distance ladder against the next, we can directly measure how fast the universe is currently expanding. That measurement is 73 kilometers per second per megaparsec. Two methods, both sophisticated, both checked and rechecked by independent teams, both coming back with the same answers, and the answers disagree. This is the Hubble tension, the gap between what the early universe predicts and what the local universe measures. And as measurement precision has improved, as both methods have been refined with better data and better instruments, the gap has not closed, it has grown. The latest results, published just weeks ago in April 2026, have confirmed the tension with higher statistical confidence than ever before. This is no longer a measurement error that might disappear with better instruments. This is a real discrepancy, and it is telling us something. We just don't yet know what. I want to sit with the magnitude of what I'm describing for a moment, because I think it is easy to hear the words cosmological tension and feel that this is an abstract technical problem for specialists, remote from anything that matters to your daily life. But consider what the Hubble tension is actually saying. It is saying that the two most powerful tools we have for understanding the universe, our model of its beginning and our direct measurement of its current behavior, do not agree with each other. It is saying that somewhere in the 14 billion year history of the cosmos, something happened that our best theories do not account for. It is saying that the standard model of cosmology, a framework built over decades of brilliant work, confirmed by extraordinary evidence, precise enough to predict the composition of the universe to several decimal places, is incomplete. Not wrong in every respect, not useless, but incomplete, missing something. And this is actually one of the most exciting things that can happen in science. A precise and undeniable discrepancy between prediction and measurement is not a failure. It is a door, a gap in the map where the unknown territory begins. The history of physics is full of moments like this, small, stubborn discrepancies that wouldn't go away and eventually forced the abandonment of old frameworks and the construction of new ones. The orbit of Mercury refused to match Newton's predictions by a tiny fraction. Einstein's general relativity explained the discrepancy, and in doing so, replaced Newtonian gravity as the fundamental theory of gravitation. The spectrum of light emitted by hydrogen atoms had lines that classical physics could not explain. Quantum mechanics emerged from the attempt to understand them and transformed our entire picture of reality at the smallest scales. Great physics is often born from small, stubborn gaps between theory and measurement. The Hubble tension may be one of those gaps. So, what might be hiding in it? What could be causing the universe to expand faster than our models predict? The honest answer is that we do not know, but there are candidates, and each of them is stranger and more fascinating than the last. The first possibility is that our measurement of the local expansion rate is wrong, that there is some systematic error in the cosmic distance ladder that nobody has yet identified, that the Cepheid variable stars or the Type 1a supernovae are not quite as reliable as we thought, that when we calibrate one rung against the next, we are accumulating an error that magnifies with distance. This was the favored explanation for years. Surely, many physicists thought, the measurement will sharpen as data improves, and the tension will dissolve. It has not dissolved, but this possibility cannot yet be entirely ruled out. The second possibility is that our model of the early universe is incomplete, that the cosmic microwave background is being interpreted through a framework that is missing something. Perhaps there was a burst of exotic energy in the very early universe, before the microwave background was even formed, that our standard model does not account for. Some physicists have proposed what they call early dark energy, a form of energy that existed briefly in the universe's infancy, accelerating expansion for a short period and leaving a permanent imprint on the expansion rate we measure today. This is fascinating and plausible, but the evidence for it remains indirect. The third possibility is perhaps the most radical and the most intriguing. Perhaps dark energy, the mysterious force that is causing the universe to accelerate its expansion, is not constant. Perhaps it changes over time. Perhaps the universe has not been expanding at a steady pace, but at a varying one, faster in some epochs, slower in others, in ways that our standard model assumes away but reality does not honor. Just this month, researchers combining data from multiple surveys of the large-scale structure of the universe have found tentative hints that dark energy may indeed be evolving, may be changing, may not be the simple cosmological constant that Einstein added to his equations all those years ago. If dark energy is dynamic, if it shifts and changes across cosmic time, then our entire picture of the universe's future changes with it. The fate of everything, the ultimate destiny of every star and galaxy and particle, depends on what dark energy does next. And right now, we genuinely do not know what it is, where it comes from, or what it will do. There is one more possibility I want to mention because it sits at the edge of what current physics can even describe. Some theorists have proposed that the Hubble tension is a sign that our theory of gravity itself, general relativity, the framework that has survived every test thrown at it for over a century, may need to be modified. Not abandoned, not replaced, but extended, corrected in some domain where we have not yet tested it carefully enough. Gravity is the dominant force on cosmic scales. The expansion of the universe is governed by gravity, and if our theory of gravity is slightly wrong in ways that only become apparent across very large distances or very long timescales, then both our models of the early universe and our measurements of the local one could be systematically biased in ways that create exactly the kind of tension we observe. This is a genuinely radical suggestion. General relativity is one of the most successful theories in the history of science. Modifying it without breaking everything it already correctly predicts is extraordinarily difficult. Every previous attempt to do so has run into serious problems. But the Hubble tension is serious too, and when precise data refuses to fit even our best theories, even our most tested and trusted frameworks, the frameworks have to be questioned. That is not a failure of science. That is science working exactly as it should. I want to close with something that I find both humbling and quietly wonderful about all of this. The universe has been expanding for 13.8 billion years. It expanded through epochs we cannot directly observe, through the era of the first stars, the formation of the first galaxies, the long, slow acceleration of dark energy. It has been doing its incomprehensible work for a time that defeats all intuition. And we, creatures who appeared perhaps 300,000 years ago on a pale blue dot orbiting an unremarkable star in one of hundreds of billions of galaxies, we have built instruments precise enough to detect an 8% discrepancy in the rate of that expansion. We have stared at the relic light of the Big Bang and extracted from it predictions that can be compared with extraordinary accuracy to measurements of galaxies billions of light years away. And then we noticed that something did not quite match. That noticing, that careful, rigorous, unsatisfied noticing, is one of the most remarkable things our species has ever done. The Hubble tension is a problem, a real one, an uncomfortable one that may require revising ideas that have stood for decades. But it is the kind of problem that only becomes visible at the frontier of genuine understanding. You don't notice an 8% discrepancy in the expansion rate of the universe unless you have already understood an extraordinary amount about the universe in the first place. The gap in the map is not a sign of failure. It is a sign of how far we have come, and a sign of how much remains. Before you leave, one question to carry with you. Think about something you understand well, something you have studied or practiced or thought about deeply for a long time. Is there a small discrepancy there, a nagging 8% that you have been explaining away or ignoring? Something that doesn't quite fit but is uncomfortable enough to set aside? What would happen instead of setting it aside, you followed it, carefully, patiently, honestly, all the way to wherever it leads? Sometimes the most important discoveries begin with something that doesn't quite add up. This is GreenTea English. Thank you for thinking with me today. See you in the next one.